going to talk a little bit about pulleys. So basically it's kind of an applied physics problem. So we got here Papa's old bicycle that we weighed in a previous video, and it came out to about 40 pounds. Okay, so now we have this bicycle storage system right here that uses pulleys to pick the bike up and put it on a ceiling so Papa doesn't have to lift the whole weight of the bike. Okay, and what pulleys do is they give a man a mechanical advantage. So as you can see, if I pull down on this rope right here, okay, I've got 4 ropes that pull up, okay? Same thing if I push up right here, all right? 4 ropes go down, so I've got 1 down, and these 2 move and pull up. So basically what that means is I've got 1, 2, 3, 4 to 1. All right. So that means that this has a 4 to 1 mechanical advantage. Now you'll notice that what I have here hanging is a weight. Okay, that weight is about 10 pounds. So if I've got a 40-pound bike pulling down, and I've got this 40-pound weight right here, or a 10-pound weight, so 4 times 10 is going to be 40. So this should be about neutral buoyancy, and it is. Okay. Now you'll notice the front end lifts up first. Okay, that's basically because this pulley is closer to this weight. But as we do this, I'm putting very little on it, and it doesn't fall back to the ground when I let it go. It pretty much stays there and will hang. Okay. So that's part of it. Okay. Now, the other thing that happens on a pulley like this, when you gain an advantage, so I don't have to pull it at the 10, at the full 40 pounds of the bike, I only have to pull it at 10 pounds. But the disadvantage, what you lose in that, is that because this is a 4 to 1 mechanical advantage, there's also a distance thing. So that means I have to pull this down 4 times as much as this has to go up. Okay, so let's kind of compare that and see what happens. Okay, so if I want that to go up 1 foot or 12 inches, that means I have to go 4 feet pulling down on that rope right there. Or if I do 12 inches on this, 12 divided by 4 is 3, those wheels are going to come off the ground by 3 inches. Okay? Okay, now to test this out, what you can see is I put a level on here to make sure that we get the bike level. I put a rule over here. Okay? So I can pull this down from the bottom here, so the bottom gets down to the 12 inches. Okay? And 12 divided by 4 is 3 inches. So if I get the bike level again, the wheel should be about 3 inches off the ground. So let's try this out as an experiment. Okay? So if I pull this down, so I get about 12 inches there, get the bike level. I should have about 3 inches on the ground. So let's measure and see what we get. That comes out to exactly 3 inches. How about that? So what did we learn here? Okay. Number 1, pulleys can either just change direction, or if they're grouped together, they can become a force multiplier. Okay. And to figure out how much they increase the force, you count the number of ropes pulling up versus the rope pulling down. So in this case, we got 1, 2, 3, 4 pulling up, 1 rope pulling down. So it's a 4-to-1 mechanical advantage. So that means if Pat Ball pulls this rope by a force of 10 pounds, these ropes pull up by 10, 20, 30, 40. So 10-pound input, 40-pound output. And it also, we learned that in order for this to move, I have to pull this rope a lot farther than what this bicycle actually goes up. Because it's a 4-to-1 mechanical advantage, I have also a 4-to-1 disadvantage in the distance. So we learned that for every foot that this pulls, it's only going to go a 1/4 of a foot up there. Basically, every 12 inches, it's going to rise 3. So anyway, I hope that tells you a little bit how Pat Ball's bicycle hanging system works and how the pulleys work. And hope you have a great new year.